you just
Thank you for coming down and helping. Oh, one other weird thing. Initially, I was like, when this wasn't working, I was going to try and poke you. So I went to chat. Where's chat? And the chat window showed up there.
No. This is
Maybe, what did I? I saw.
because you have two
Oh,
different view
that's it.
here.
I clicked on that, and then I.
This side,
Yep,
or
and
the
then I
view bar
typed in.
opens
Yep,
on this side, and the
that's the
other
problem. I'm used to seeing chat and participants in the same place. So okay. In that case, that should
because
be
you
being
can
secret.
chat and
Yep.
participants at the same time.
So it was just being secret because you. Whoa. So hello everybody. It looks like it is now 10 a.m. local time. We'll give people another minute or two to wander in because people are still figuring out where the room is, etc. Wow, there's really bad noise isolation between my keyboard and the microphone. Not very well, but yes. Oh, I should probably have some sort of idea. What water people are in. Clunk. Hey,
There's one too many F in the name of Thomas Calf.
crap. So there is. Oh well, it's Thomas Graff today. Yeah. Thank you. Alrighty. So, hello everybody, and welcome to IEPG 118 at IETF 118. So IEPG is the Internet Engineering and Planning Group, and this is a sort of unofficial thing that meets before the IETF actually starts. It's supposed to be more operationally focused than most sort of IETF meetings are or working group meetings are. And hopefully we will have something interesting to talk about. The agenda is often filled with DNS and BGP, but this time it is somewhat different. We do likely have some extra free time at the end of this. So if anybody wants to talk about something, and has an interesting presentation, we might still have time. We are officially in the Warren waffling for a little bit part of the presentation. Somebody pointed out that I missed that there's an extra F in Thomas's name. I apologize for that. But this is our agenda. Does anybody have any agenda bashing? Did I miss anything that I was supposed to put in and didn't? Nope. Is this thing on? Great. Alrighty. So without further ado, we will have Mr. Jeff Haas talking about packet discard reporting. Oh, I will mention this is the new Meet Echo interface, and so, um, you know, who knows if we're going to get the buttons right. Um, Okie dokie, let's get going.
Good morning, everybody. I'm Jeff Haas. I am here to talk on behalf primarily of John Evans, who's the main author, along with Alexander, about some thinking about what to do about packet discards and interesting things we should be doing about it. This presentation will also be given in a slightly different context at OPS-AWG. I'm here primarily because this really is intended for operators, and we're trying to get people involved in what we're doing here. So we've had a lot of presentations the last couple of IEPGs about things that happen when traffic is getting discarded and you don't know necessarily why. A lot of those have been in the context of very strange IPv6 things, but if you're an operator, you're often chasing down, why is things just falling apart to my network? Where's the packets going? Where are they dropping? And the problem is finding these things can be challenging depending on context. The whole purpose of a network is to get the packets from A to B. And packet loss is the one bit of signaling we have that the network isn't doing its job for some reason. And the challenge here is packet loss is some regular portion of what the network's supposed to be doing anyway. If it actually doesn't get there, maybe it's not supposed to. You have things like discard routes, you may have firewalls, but for the most part, if you are really expecting traffic to get around, you want to make sure that it is, and when it doesn't, that's interesting. Maybe you should do something about that. So the goal here is, how do you minimize the anomalous cases, things where packets are supposed to get through and they don't. And this is the standard feedback loops you expect off of trying to actually do something about packet mitigation for losses. If you're an operator, you're paying attention to some sort of source of data that's telling you that something's going wrong. You are ideally doing some level of organization of that information to help you figure out what it means. And then hopefully that methodology you're putting together will tell you that you should go do something about this. And this is, again, where I'd say, please talk to John when he gives his presentation at OPS-AWG coming up later this week, because this is not theoretical. John and Alex are actually doing stuff with this inside of their network at Amazon at scale using automation. So this is not just some theoretical bit of information model we're talking about. This is some steps to try to actually make these things a little bit easier for operators. Second half of the problem statement, how can we actually report the packet loss? And the challenges are, what are the accuracies that we're looking for? Where are we getting the data from? And then, of course, you have to provide enough context. This is all about organizing information. Where is this at? What is the cause? Is the cause something that's in one of the bins that we're tracking? And based on that, is there something specific we should do about a different type of these things? And again, motivation here is they are actually taking this information and using this in a backwards fashion for reasons to trigger mitigations. And for the most part, there's only a small number of mitigations that they have in their specific bin. We have sort of overlapping work that we've been discussing from Juniper, where we're actually, Warren, we are judging you for your ringtone. I have some overlapping work inside of Juniper where we're actually now getting deep into the hardware and talking about, well, we have programming errors and this is a class of things. Well, they're not trying to do something quite that deep at this point. They're a little bit more vendor neutral. And for the most part, this is the kinds of things that as operators you're going to do when you start seeing some box or some link in your network being crazy. You're going to take it out of service in some fashion. And for the most part, it's the usual thing. take the whole box out of service, take a link or set of links out of service. If you think that this might have been caused, due to some correlation to something you did, roll it back. If you have your favorite traffic movement technology, depending on what you're doing, this is obviously a group that we talk a lot about BGP. We know what a lot of those things look like. You may put your box into IGP overload. There's all sorts of things. And certainly there's push the button and say, hey operators, something's going wrong, go look at this. So since this is intended to be used for automatic procedures, signaling of this information and being precise about what you're doing so you don't take the wrong action, especially if you're auto mitigating this, is important. So what do we have in the current IETF bin right now? Unfortunately, not terribly a lot. Out of SNMP land, we have ancient IF table MIB stuff that says we have discards and errors, and this is what we've been binning stuff in for years, and it's not terribly helpful if you're trying to do anything that's even the least amount subtle. But it's the tools we currently have. One of the discussions we have as we're working our way through stuff in Yangland is should we be doing newer and smarter things? And maybe this conversation starts kicking off some of that discussion. We also have the problem that if all of you who are running things like IPFix, NetFlow, etc., you realize that between all your various types of reporting infrastructure, SNMP, CLI reports, that vendors don't necessarily bin the same statistics in the same locations. What's going on here? I'm seeing discards. Are these things discards versus the firewall counter? Are the discards versus packet drops because you have a routing failure? This is part of the headache. And another sort of motivation for this discussion is, can vendors do things that are a little more consistent with each other? Maybe make the operators a little less crazy. You have enough craziness of your own. You don't need to come in from the vendors itself. Important part is trying to actually bin things in consistent categories. So not every single discard is exactly the same. Some of these things, are they full failures? Are they grayouts? Are you getting duplication? Do you see things like a interface and a sub interface are binning things the same way? And your counters, as I like to yell at my own developers, if these things don't add up to 100, they're going to drive people nuts because they're going to be wondering what's the real truth here. What happens if the reporting mechanisms across platforms, if you're using things like SNMP, are giving you different levels of the same statistic? And of course, just nibs in general are not good granularity, as we got done talking about. So semantics for the packet loss reporting just really are not clean. What should we do about that? So again, John and Alex, they spent their time defining some classification scheme. This is the primary thing they want to talk about, which is ideally the seed for future work. They defined discard classes, again, working backwards from the things that are interesting for them from a auto mitigation situation. They're spending their focus on defining the semantics of those discard behaviors. And most importantly, they have, across a number of vendors, I'll let them actually get the precise number at their own microphone, actually have gone out and implemented this via various mechanisms, anything from scraping the CLIs of the various devices to getting down to the hardware levels when it made sense. And they basically have categorized these things into a large number of categories. This is the actual meat of the proposal here. It's just what we would call an IETF, an information model. And my suggestion to them as they were working through the draft semantics, agreed to help them sort of wrangle the IETF into things, is put together an information model, get a little bit of agreement about among people that actually care about this stuff as to how we actually track these things. What do you want the vendors to actually try to put these things in the same categories? Their own opinion about this, they do this today. This is the scheme that they are actually using. This is not some just completely vapid model. This is something that they're using for their own purposes to trigger their own infrastructure. And again, where you put things is incredibly important. There's a draft here. Please take a look at it, see what you think about it as operators, how you actually want to organize stuff. Again, there's a presentation, ops to AWG. They invite additional discussion. And the purpose of this is not to end at the information model. It's to take this along the next couple of steps. And we're either at end of presentation. No, here we go. And again, the steps for their purposes are eventually, how do you take these various types of binned categories and decide that you're going to use these as triggers for remediation of stuff in your network. Again, there's at the very fundamental routing layers of things, they're taking devices, links, etc., in and out of service. Juniper land, we're also looking at these things for like hardware programming black holes and seeing, can we actually fix those sorts of things? Any of you have suffered from a stuck fib queue of some sort, understand the pain of this as well. And again, this is not theoretical. This is stuff they're actually doing. So the challenge for all these things is you have a number of vendors, a number of platforms, a number of ideas about how the forwarding pipelines actually look like and how discards manifest within that pipeline. You have to limit the number of categories you're actually doing these things for. So is that model that was displayed the right model across the industry? It's working for them. So the challenge becomes classification of these things. And some of these things are probably good categories to expand on outside of these very simple model things, like TTL expires as an example. Are those things that are related to your tunneling protocols? CPU issues related to firewalls? Is the null route that you have in there because of static configuration, aggregation, something else? How do these things actually manifest? And at the end of the day, and especially if these things are driven by CLI behaviors, you can't actually detect these things context-wise unless you know what the impacts look like. And that can be challenging on a per vendor basis. So again, there's an information model in there. Data models will come later. The discussion point eventually is, what do we do with this stuff once you agree on what these things look like? And again, this is something they're practically doing today. This is something they would like to see more people doing of their own work. And for people that are vendors, could we actually provide infrastructure for this? What does that actually look like? And an example of that could be we maybe take these info models, put them into Yang, so that you have a consistent way of querying these things, or have them stream through IPFix. How do we actually get this stuff off the box? And then, of course, at some point, the secret sauce about what you do with these things from a DevOps standpoint, absorbing this information, deciding that something bad enough is happening, and taking network elements in and out of service, that becomes just another part of programming your network. They also did an analog presentation, so that gives you a little bit of stuff to look at, a little bit more practical than me waving my hands up here into the microphone about something else that they're doing. And I think that is the end of the slides. So again, the request here is, as operators, these things are pain points that you're dealing with. Take a look at the info model, see if that fits your own triage procedures, and if not, maybe think about what they should look like. Talk to John and us about what should go into the info model, and then hopefully after a little bit of work, we'll decide there's some small amount of effort to put this stuff into Yang, put this in IPFix, and maybe start pushing vendors to implement. That ends the presentation. Are there questions?
Benoit is in the queue.
Hi, Jeff. So it's on?
Very
I
quiet.
think so.
It's on. Okay. Thanks, Jeff. So I think this is interesting work, specifically to get some consistency. But what I was sharing in the chat is that we've got the IPFix forwarding status information element, which contains a lot of the reason. So it could be consumed, it's management, it's forwarded, or it's dropped. And the dropped, you've got already a lot of reasons, like ACL DNI, drop, unroutable, adjacency, BAT TTL that you mentioned. So that's already what we started to do. So this is somehow similar. It doesn't do L2, right? It's L3 only. So there is at least a step in the right direction. The advantage of IPFix is that you could define this for whatever key field you want, so for your own flows.
Exactly.
Thank you.
And one of the discussions that's happening is, as you're saying, some amount of the stuff has some amount of standardization. The Juniper work, as an example, is a little bit deeper into the forwarding pipelines for the the hardware, for detecting the specifically black holing type situations. Figuring out the overlaps and not just adding more counters to add more counters. We don't want to do that. We want to make sure that the counters are really consistent, they fit into the model, and if picking any one of these items, if that is the correct way to expose that piece of data, that's the right answer.
So more just a comment than a question. I don't know. I'm going to click share screen. It's probably going to die. So like share screen accept. So like here is the IETF. Is that presenting?
No,
it's not going to show up. There we go.
There we go.
So like here's some pretty charts and graphs from the IETF meeting network. And there's some spots where we're losing some packets somewhere and we've got no idea. Like the closest graphs I could draw was interface errors and interface drops, and there's some set of numbers. Having better counters and stuff would be, I think, useful for that.
Having the NOC actually throw in their opinion would be great. And keep listening to Benoit here, maybe you already have statistics you should be gathering.
Cool.
Okay. No other questions? Again, Ops AWG coming up later this week. Look up John. He's absolutely going to be here, and he wants to talk to you about where we take this forward. Thanks.
Awesome. Thank you. And next we have, I believe, Thomas Graf presenting on this. Time. I'm assuming you will drive your own clicker thing.
Yep.
Cancel timer. Let me just start a new timer for you.
Okay.
Good morning, everybody. I'm Thomas, and I will be presenting with Vincenzo together. Yeah, very similar topic than Jeff was just presenting before. We are talking about network anomaly detection. So we want to bring all the different metrics together, and also by collecting more and more incident data from networks, we realized that we need to get better organized in order also to optimize network anomaly detection, so that at the end, coming from a knowledge-based anomaly detection system, we can go with that additional annotation, semantics, more towards supervised and semi-supervised machine learning.
There we go.
The challenge of today's network provider. So first of all, what we monitor are routing tables, VPNs. We do that by taking data from the different network planes described in the network telemetry framework. We as operators are not good enough, not fast enough. So usually when outages are happening, we can see that the scope of the outage, the severeness, and also the duration is getting longer. So what we see here clearly is that network operators lack visibility. And I think Warren just showed us in the IETF network, we don't know why we are dropping packets. That's bad. Collecting data means also we need to get organized. So in a big data architecture, we organize data in so-called operational and analytical data. So for us in networks, operational data means network data which we collected through network telemetry, where we have clear defined semantics, where in analytical data, here at IETF, we are starting to standardize semantics, and one part we bring in is that we do the annotation of anomaly detection data we want to standardize, and I will later explain why. First of all, what is anomaly detection? It is in a nutshell, basically, we are monitoring changes in a network, and our concern is whether those changes in the network are actually impacting customers or not. And from there, we want to get analytical insights in order to do the next troubleshooting step to go down to the responsible network platform or network node where the traffic is being dropped, or for instance, the topology change was being originated from. We already presented a paper at the Applied Network Research Workshop in IETF117 in San Francisco, and there is soon also at IEEE coming a more detailed paper on how using anomaly detection in a network environment. Our motivation of this draft is basically to, through network incident postmortems, we as network operator want to learn and improve. And by collecting that network incident data, we understood soon by having more and more such data, we need to get better organized. We need to start to automate the post-mortem process. And one of the first things to do that is actually have well-defined machine and human readable metadata semantics so that we can draw some conclusions there when we perform testings with network anomaly detection. And also to get further organized, it's not only about collecting that metadata for our own network, because one network operator is still not having enough incidents by itself to get enough information to further improve. It's better to actually collaborate among the network operators and also among academic research to exchange this labeled data and improve the research on this area. So Jeff brought a very good example in terms of we not only want to understand that we are dropping, we also want a little bit know why we are dropping. And the same thing you can do with other network protocols as well. Just giving an example, when I withdraw a reachability, I might want to know from where the withdraw is coming from or why the withdraw is coming from. Anomaly detection can tell me that at the same time a peering went down, but the causality that the peering went down, and because of that I'm withdrawing the reachability, that information is actually quite difficult to obtain. So getting additional information like what Jeff just described before really helps an operator to draw this conclusion. And also anomaly detection can also bring some insights or what's happening at which point in time in the network, and gives us some insight whether this could be related or not. So I hand over to, sorry, one more. So first question to the network operators in the audience. Is this something interesting for you to understand why, for instance, packets are being dropped, why reachability is being withdrawn? So getting the causality of those network operational metrics. To the network vendors, is this something which can be obtained from the network process? So for instance, a BGP process, the trigger to do a withdrawn, do we understand why we are withdrawing that reachability? Is this something obtainable on the network device? Can we even maybe generalize this among different operational metrics? To the academia, if we would have labeled operational and analytical data from a network anomaly detection system describing whatever operational metrics are an anomaly or are normal, would that help your research to further improve network monitoring? And to everybody in the audience, having well-defined symptoms. With symptoms, I mean, for instance, the action that we are changing a topology in the network, changing the interface status, or also having a drop spike in the network due to congestion. Would that help in the exchange of data among the different operators to improve the network anomaly detection systems?
Thanks, Thomas. Sure. Morning, folks. Just to bring in a little bit of a machine learning point of view into the discussion, as we are speaking about anomaly detection, right? If you you can define an anomaly as a change which can be concerning somehow. So if you speak with the machine learning community, you will find out that there are many ways to classify anomalies, and one way is to divide them in global, contextual, and collective outliers. And if you speak with the networking community, you will find out that most of the anomalies we are interested in are primarily collective anomalies, which means these are those anomalies that if you want to spot them, you have to look at multiple metrics or multiple measurements across the whole network. And this is way more important. This is very important, especially from what from the point of view Thomas was mentioning before. So an anomaly can actually propagate across multiple planes, and you want to be able to track that and track somehow the causality which goes from one symptom to the other. And this is one of the reasons why we have been working on defining this young data model, actually two data models, and the way we are structuring this is by defining in two different entities, as symptom and incident. So when we speak about the symptom, what we have in mind here is something like, we are describing what changed in the network and what is the reason and the cause that might have generated that change, and what is the concern score, if you like, so what is the degree of concern we have in relation to that symptom or that change. We use tags. We add tags to the model, which are there for describing network plane, which action, which reason, and which cause was observed during the symptom. And pattern might actually help, like spotting particular type of patterns we identify in the symptom, things like a spike, a drop, or a mean shift, and so forth. And there is a source there as well. Like why the source is important is because you can think of this model or as an exchange mechanism between not just different human beings or network engineers which are trying to explain symptoms to each other, but also to exchange information between a network expert and a machine learning algorithm, trying to say, you can create labels and use those labels to train the algorithm, or you can get the output of the algorithm and validate this output through a human eye. And this is the reason why we have the source there, which we specify if the symptoms have been defined by a human or a machine learning algorithm. And the other entity, which is more on the analytical side here, is what I was calling the incident. Even in this case, like an incident can be defined as a list of symptoms, a collection of symptoms which are seen together. So again, you're trying to find like the correlation between all the symptoms together, and you mark that as a single incident. So just to wrap it up, we are very much looking forward to getting some feedback on this from the audience. We hope it's clear like why having a standardized and consistent way of exchanging information in relation to anomaly detection in networks is important, especially between different actors. And we would be very happy to have the possibility to have a working group with heterogeneous people, like from vendors, academia, and operators, such that we can together define a semantic structure and an ontology maybe for defining network symptoms and for operational and analytical data. Hopefully, this work can also help identifying any missing information that we can get from the network to make this even better. So thanks very much for the attention.
Tom's in the queue. Okay.
Hello, Tom Hill from BT. I actually quite like this work. I think it's quite interesting. I do have one perhaps philosophical problem. I wonder whether or not, how much are we asking an individual device which effectively exists on its own in the world? How much are we asking it to infer? So we're asking that particular specific device on its own to determine a certain amount, or to infer a certain amount of things from other events that it can see. Do we trust it to to not make mistakes? How much can we trust something to not make very obvious overt mistakes that a human, or even a system that had a view of all of the routers, all of the end devices?
That's a very good question. So what we think is there is not one way to actually get a precise visibility from the network. You need multiple angles. So one angle we see is with the collective outlier. We are observing basically from the three different network planes what is really happening in the network. On the other side, we believe that those operational network telemetry metrics itself, we could get more additional information, like what Jeff basically showed us, that we get more information on the causality. Having those two things together, the outlier detection itself, which tells us this might be related, and getting from the devices in some areas where it's reasonable, also getting the causality, we believe that's probably the best way of looking at the network.
So in effect, you still expect to have a super system that can understand holistically what's going on, and it takes clues from devices based on the metadata that they have generated from inference.
Exactly. Or to very simplify, what I believe is basically a single network node, a router, does not know the entire network.
Okay.
By getting all the information from all the devices from the network, getting that on a central place together, perform anomaly detection or some sort of analysis, you look at the network as a whole.
Yeah, I can still see a situation where if you have 14 devices, 13 of them think one thing happened, and then one device that actually knows what happened because it was the only one that could tell. Do you believe the 13 or the one? And that's the thing that I think starts to bother me, is that if we start scoring this based on a bunch of routers that don't know anything.
Exactly.
So we have to be very careful. But thank you, it's an interesting piece of work.
Thanks.
Jeff has two things, sort of supporting Tom and having worked prior for Arbor Networks years ago. His point is very valid that it usually takes the network, or at least analysis of the network, to come up with anomalies. So this is a good reporting format for the network, fleshing it out based on those sorts of things be good. The real reason I'm here at the microphone is to ask either Warren or somebody else in the security area. I have a vague memory of a working group that was closed, that was being done recent-ish, that did the security ticket analysis framework. Now it's basically for automated ticket reporting. That's
Woohoo! I knew something.
So I didn't actually track the work terribly much. I glanced at it in the beginning because of what I used to do. Doesn't that overlap a little bit in the sense of it had to come to some sort of conclusion that something weird was happening before it threw out a request?
I think that DOTS was more just signaling of stuff to a mitigation service, being like, please mitigate my thing. Although Jen is shaking her head, so okay. I think it was more just like, I've got a mitigation service, I'd like to tell it, please block these sorts of things. I don't think it had, as far as I remember, much, magic automation. And
not a lot of analytics, but it was reporting. Okay, thanks.
Jelenkova, to this point, I think like one man's anomaly, it's another man's normal mode of operation, right? So I guess, yeah, I do not believe we can anytime soon like have 100% artificial intelligence or machine learning ability to detect. But I think, yeah, you will need to, I guess, adjust each event eventually, right? And understand that for that type of events, you would trust one kind of devices more, and for another type of events, you could not trust anyone. You just probably still need to send everything. And to people, yeah, because I think it would really depend on the network topology and what's happening in the network, right? Because from my experience, I cannot sometimes tell if it's okay or not unless I looked deeper and not actually in the network telemetry or anything from routers, but other systems like what kind of maintenance I have scheduled, what kind of like I might have like I don't know like conference in the building, which would look like anomaly in the traffic level, right?
I
And
mean,
it's something you would not never get from machines, right? You get it from talking to reception people and find out, oh, we have like so many users today, or like something.
there's a well-known example of a massive traffic spike that a bunch of people saw because the Italian Grand Prix had just started. And like, there is no way that a network anomaly detection would have that external info.
Yeah, I've seen many cases here when you cannot tell if it's a DDoS or it's some event and people now want to watch the news, right? Or it's Apple released an update and all laptops decided to go and download them at the same time. It might be DDoS or it may be normal mode of operation. Yeah, so I agree. I don't think, there is a like silver bullet for this, but I guess, it would be really nice to have more data in some centralized system and teach it and introduce some custom rules for each network, maybe, right? How to process those rules and what kind of signals, yeah, we want to look. Because, I guess your rules might be completely different from mine.
So again, I think philosophically, I like philosophy. These devices are pretty stupid, right? They're not very intelligent. There's no AI, right? And instead of adding any form of intelligence or any form of insight, we're just asking them to take a bunch of events and infer something from it. Now, can we? I mean, just one example. Can we trust any router, particularly if you've got a whole bunch of them that are all running the same software version and all have the same bugs? Can we trust them to infer something from their own fib programming bug? You know, if there is a situation in those cases where all the routers agree and they say it was this problem, actually, is it realistic that we can trust them to infer that correctly? We've got to remember that if any system that has a view of multiple things, including a human or a robot, is a god amongst routers. They are blind, they don't know anything, they only see what they can feel, and that's it. So philosophically, is it reasonable to suggest that we ask them to infer more things and we trust them to infer more things when they really don't know anything anyway? And is it valuable to trust that information in a learning model, or is it going to set us up to fail? It's a really brilliant thing to start discussing. I'm not saying it's wrong in any way, shape, or form, but fundamentally and philosophically, I don't know whether or not we can actually benefit from asking a router, an individual router, to make its own mind up about something.
What I can say is now doing for a little bit more than a year anomaly detection on Swisscom's network, and we have approximately 14,000 routers onboarded. And doing anomaly detection, I can say that from the beginning to now, our insights changed. So like certain things which we thought in the beginning, well, that just happens maybe once and might be something special. We later, the more postmortems you're doing, the more insights you're gaining from the network, you see that there are commonalities among those different incidents, and you start to see that there is some pattern there. There is something to be learned from. And I really believe by open up the scope and actually not having only one network operator doing those insights and starting exchanging the data among the operators, because maybe one type of incident happened at one operator and it's going to happen in the future on another operator. We can learn from each other, and doing that in a pragmatic, sophisticated way, I think, in my opinion, that's how monitoring could be improved.
And if I can add something here, sorry, if I, just to add one note, I think you can see this as the beginning of an iterative process where, you know, the network engineer can drive the learning process of automated algorithms. You can iteratively review the results you get, validate them, and refine the metadata that, like the one that as we described, and you can provide that back to the system, which can learn from your feedback. So it's also a way to help the machine, which at the beginning might be completely ignorant about the network in general, and kind of train the machine iteratively. That's another way to approach it, if you like.
Great, thank you. That's fascinating. Alrighty, and we have one more presentation today for your viewing pleasure, and that is Mr. Jeff Houston on Starlink protocol performance, which, seeing as I now have Starlink somewhere, will hopefully be interesting to me. Would you like to drive the clicker, sir?
You can drive it.
I can drive it.
Hi, my name's Jeff Houston. This is not a talk about the philosophy of network management or whether there's a god of routers or not. Thank God. This is actually a much more pragmatic, experiential talk because a number of colleagues of mine have installed Starlink. Bizarrely, one of them lives in California, where evidently the wired connectivity is complete shit. And the only way that he can get decent connectivity is to actually go up, which I find bizarre, but nevertheless true. And the other one is my boss, who has some property out in, if it hasn't burned down already this week, somewhere in Outer Whoop in Australia. if the dish hasn't melted, I think it's still operational. And this is actually about the performance of Starlink. Next slide. Because its build, are you moving this forward?
Yeah.
Oh, okay.
You didn't say next.
I did.
Did you?
Did I say next slide?
Yes.
Thank you.
I didn't hear him say next slide.
Let's all say next slide together. Next slide, Warren. So just a little bit of physics. Low Earth orbiting satellites shelter behind the Van Allen belt. That way you can kind of not worry too much about protecting those spacecraft from solar radiation. So the highest you can go is around 2,000 kilometers. Once you get higher than that, they start to get far more radiation, and you've got to do a lot more protection actually on the spacecraft itself. If you go lower than 160 kilometers, you run into two problems. One is you run into the upper part of the stratosphere and you start to generate some heat and you start to lose velocity. The other thing, interestingly, is that at some point up there, Earth geography stops and you become outer space. Now, all the countries in the world have agreed that outer space starts somewhere up there, but none of them have agreed at what altitude. So some countries it's 100 kilometers, some it's 120, and oddly enough with some it is indeed 160. And so if you, at about 160, as long as you don't communicate down, there are no laws. You're in outer space, you're in no man's land. Lower than that, no. Somewhere, someone on the Earth, someone might claim that they earn the bit above themselves. So LEOs are kind of in that first part of outer space. So as I said, high enough to stop them grazing, but not so high at the Van Allen belt. At 550 kilometers is where Starlink have decided to station. Now, the geometry of that is your 3.7 milliseconds up and down. So a full round trip, which is 4, is there for approximately 7 milliseconds. If it was on the horizon, absolutely on the horizon, which is almost impossible, it would be 2,700 kilometers away, but it doesn't quite work that way. The visibility of Starlink is from 25 degrees up across 25 degrees. And at that level, the round trip time is about 11 milliseconds. Next slide. Oh, previous slide. There's a lot of them. I've got that on the slides there. What is it? StarWatch, the StarWatch app. There's a whole bunch of these apps that simulate these things around the Earth. Starlink has decided to go approximately eccentric. So most of the spacecraft are between 56 degrees north and 56 degrees south. But you do find a number of them are in polar orbits, predominantly, I believe, to pick up Prudhoe Bay and the oilers up there, giving them service because they pay big money. The other thing that also happens is that Starlink, when it launches a vehicle, releases just a canister of these satellites. And you'll see on this map, there's one of them there, just a train of these things. Over time, they distance themselves out. So that's why you actually see those trains going. Next slide, Warren. So this is the basic geometry of the Earth station to a satellite. 550 kilometers up. It'll span a circle of a radius of approximately 900 kilometers. Because at 900 kilometers away, it's 25 degrees up to get there. So if you think about it, a footprint with a radius of 900 kilometers is a 2 million kilometer radius, a 2 million kilometer area of the Earth's surface. If you say how big is the Earth, well, you need 500 of these spacecraft evenly spaced, and you'll cover the entirety of the Earth's surface. That's stretching everything. Reasonably, to get decent coverage from a LEO, you need between 6 and 20 times that number. So next slide. Starlink are now at 4,700 or so in orbit. Their current filings with the FCC point to 12,000. They continue to file, they continue to launch more. The thing is with Starlink, and I'm not sure if I got this on the slide or not, because of the reusable vehicles, the cost per kilogram of payload into orbit at 550 kilometers is approximately 1/10 of everyone else. They're cheap. They're cheaper than we've ever seen before, and they're cheaper than everyone else. So this is why, you know, they've got 4,276 a month or so ago, and that number will continue to rise to at least 12,000. And if they continue to file with the FCC, it will rise even more because there's no laws, go for it. Next slide. So this is the other view. And it's actually better as a GIF, so what the hell. And I spent a lot of time animating this. If you look up, if you look at 25 degrees and further, at any point you will see between 40 and 47 spacecraft whizzing over. Effectively, they will take 3 minutes to go across your visible space. So they're moving relatively quickly. So what you actually see, oh, it's too hard to do it. What you actually see is a whole bunch of these things, no matter where you're on the Earth, basically moving over relatively quickly between 56 degrees north and south. This is California, this snapshot, and that's enough in the north. The top, you actually see the 56-degree point. So most of the satellites go up in the far north, and then they start going back down again. And what I've captured there, oddly enough, is a train of satellites that are in a polar orbit. Next slide. So you've got to track them. And they swing across in 3 minutes, which is really quick. Now, Starlink actually use a much more constrained tracking system. That dishy will track a single satellite for exactly 15 seconds. And it starts at 2 seconds past the minute clock, and it'll swing to another one at 17 seconds past, it'll swing to another one at 32 seconds, and swing to another one at 47 seconds. And that's orchestrated by Starlink. So they basically instruct both dishy and the satellites where to lock in. The satellite, the dishy on the Earth, locks into the satellite by phased array focusing. And for each lock, it has to lock for 11 degrees of arc, and then it does another. Next slide. And you can see this. Because what Starlink do, they don't tell you which satellite they're tracking, but they do give you a one-way latency measurement. So if you throb away at the Starlink modem saying, what's your latency value? And you do this really quickly and constantly, and then you apply UTC timings to this and look at the minimum latency for every 15-second slot, you can actually see the point where you lock into one spacecraft, follow it for 15 seconds, and then lock into another and follow it for 15 seconds. So the blue line is the recorded latency. The red line is the minimum latency for that slot. And I'm kind of wondering now, because, you know, why the variation within that 15-second slot? And there's kind of two reasons why this happens. If you're following something from 25 degrees up 11 degrees of arc, you will get some difference in latency, because as it moves closer upwards, it's getting closer to you. So there'll be a slight variation in the RTT. So you should find there are some intervals where the latency either monotonically goes up or down. I can't see it there. The other thing is other people. You know, as Jean-Paul Sartre said, hell is other people. That's my philosophical contribution to the morning. Hell is other people. And for latency, hell really is other people. What you're actually seeing here is a bunch of other people's traffic. This is California. Wired infrastructure is shit in that place. And there's an awful lot of Starlink, evidently. And what you're seeing is everyone else's contributions to your particular hell. So it's pretty busy in terms of latency. Next slide. So how does Starlink actually work? Well, each spacecraft has 2000 megahertz of spectrum, splits it into each channel. Each channel is 250 megahertz each. They use 3 downlinks and 1 uplink antenna. Each one does 8 beams and 2 polarizations, so you get 48 beams, all steerable. Each spot will deliver up to 200 megabits per second, but if no one is beside you, you can steer those adjacent beams to you. So at any point, you can actually get up to 800 megabits a second, as long as you make sure all your neighbors have the power cut or something. They're just not there. So they will adapt and adapt pretty quickly. So you get this kind of beam forming going through where you can actually borrow from your neighbors if they're not active. Next slide. So how do you do this? Well, first you need a Starlink. But secondly, there's some really neat little tools, because if you actually use the gRPC tools and just throb away at the modem as fast as you can, you get 3 metrics which are interesting. The downlink throughput, which is not what it achieved, it's basically the carrier signal. How much capacity is Starlink aiming at you right now? What's the scheduled capacity? That varies, not by 15-second increments. It seems to vary about 10 to 20 times per second. So it's astonishingly high frequency variation. Why am I telling you this? Because at some point we're going to talk about protocol behavior. And what I'm really saying is, unlike fiber or wires or anything else you're used to, nothing is stable in this environment. So uplink and downlink change constantly. And that's what they call a pop ping latency, which is the number I've been showing that actually shows the latency of when you track onto different spacecraft. Next slide. So let's start putting this together and graphing it. This is over 1 hour. And the one thing you notice, latency, never constant, never stable. It's just constantly throbbing at 15-second increments in large steps, but below that, very high frequency. Secondly, that reported bandwidth, all over the place, literally all over the place. Next slide. Let's blow it up a bit. And even when you try and reduce the magnitude, you see this extraordinary amount of variability inside Starlink. Next slide. So now I've gone right down into a small number of seconds. And you can see on latency, the 15-second lots, but look at the bandwidth. Even when I look at just a minute, the available carrier bandwidth is constantly changing. This is like 5G hell, where you get some channels, then you get a few less, then you get a few more, a few less, and it is just constantly changing on you. Next slide. So when you've got that as your carrier, how well can you perform? So the first thing I did was bring up speed test. Why? Because it's really easy. Speed test is not TCP. I think it's packet pairing. And so when I run speed test, it kind of goes, well, across a relatively large period, this is about a month or two, you should get between 100 and 150 megabits per second day and night on the downlink, and the uplink in red, about 30 megabits a second, right? Because, you know, speed test never lies. Except when it does. Next. Next, Warren. And the latency number, well, that's what we said before. Latency of around 50 milliseconds. I'm not sure why, by the way. It is only round trip time 7 milliseconds away in propagation. And there's another 40 milliseconds of, we've just held onto your packet because it's ours. And we're not going to let go of it quickly. We're going to hang on to it for quite some time. So there's a huge amount of a latency bank inside Starlink. So that's what SpeedLink says. Next slide. Speed test. I'm not sure I believe speed test. So what I did was something a little bit different. I do a ping every second. One ping every second. And that's 24 hours. So what you notice is of those 86,400 samples, and it's precisely every second, there's around 4,000 single packet drops. They're not clustered, they're single packet drops, right? And the second part is the jitter is extremely unstable, but we knew that anyway. So you get micro drops and unstable jitter. Next slide. So, okay, let's start moving data. You've got three choices out there today. You've got Reno, you've got Cubic, and you've got BBR. And this is kind of the theoretical performance if you didn't have, you know, a large amount of loss and you didn't have a large amount of jitter. The first one is Cubic, the blue line. And what you find is that Cubic starts to stabilize at a point where it believes it has available capacity from the link. And then it slowly ups the pressure until it gets to packet loss, congestion. Once it gets that loss point, it then does a rate adjustment, the congestion window collapses, it drains the queues and starts all over again. So you get that classic behavior in the middle of that slide, which is the signature of Cubic. Reno is simpler. Additive increase, multiplicative decrease. As long as you don't get packet drop, you increase the window by 1 packet every RTT. When you get a drop, you halve it, red line. BBR, there are no buffers. BBR runs blind 7/8 of the time. So for 7 round trip times, it goes, I know what the rate is, I'm just going to send. I don't care what the drop is, I'll just repair on the fly. I'm not going to change my rate. Every 8th RTT, it ups its sending rate. The original model, BBR1, was up by 25%. So it kicks hard into the buffer. If everything works fine and I get back all the acts, you go, yahoo, let's go faster. If you have a bit of a problem and you lose some packets, which, you know, is not surprising, you just kick the network in the head. Who was talking about every packet loss being a problem? They're not running BBR if it is, because BBR really pushes every 8th RTT as hard as it can into that loss point to see if there is loss. It'll push very hard. BBR is very aggressive in that respect. And as you notice, it maintains constant pressure in theory, just constant pressure, but there is no buffer formation. It's a beautiful protocol. Next slide. So let's run it on Starlink. Now this is this same link that speed test says, oh yeah, 130, 150, no problem. Bullshit. Because when Cubic comes along and the red line at the bottom is when IPERV3 reports a packet loss event in that second. The blue line is actually me reconstructing the actual bandwidth packet by packet across RTT intervals. You actually see a small amount of a standard Cubic profile right in the middle, where it comes up, stabilizes, and starts to kick forward. But as soon as you get loss, and don't forget, this is Starlink, loss happens all the time, you never get it long enough for Cubic to actually run fast. And right at the end of the minute, Cubic is on its knees. It's all too hard. I'm going to run at a couple of megabits per second because, you know, I just can't open the window. Next slide. Next one, Warren. Good. Quick. Now, it's very hard to say that there's a standard version of congestion control in Quick. They all say it's cubic, but I'm not sure they're all actually implementing the same cubic. In fact, I'm pretty sure they're not. And so whether you're running Quiche or Pico, and so on, Pico Quick and everything else, I think they all behave differently. I'm actually running Pico Quick inside a tool that I found, thank you GitHub, QPerf. And oddly enough, it starts with a really aggressive initial window size, 10 packets. And you notice that for a little bit of time, it's just jammed the network and jammed the buffers full, but the loss event is overwhelming. The red line is just kind of going, oh, I'm not coping with this. And so immediately, Quick backs off like crazy, and within 10 seconds, I'm back down at 30 megabits a second and falling, and it never recovers, just never recovers. So in some ways, it's actually worse than the cubic we saw before, and I think the reason why is I'm not sure that this implementation of cubic is that robust. It's just subtle variations in timers. Not impressive. Next slide. Then we come to BBR. BBR always amazes me that A, not everyone is running it all of the time, and B, why not? Because look at that loss rate. It's constant. And look at what BBR says. Don't give a shit. I'm just going to run right through this, repair at speed. And the other thing BBR says is, okay, you're going to constantly vary the available capacity. Not a problem. I will constantly vary according to what you're giving me. So BBR, that looks a lot more like the capacity that you actually get from Starlink. So next slide. The moral of this story, which is where I come to the end, is if you really want to use Starlink and make it sing and dance, you've got to run BBR. Standard protocols, Reno behaves like a real dog. I haven't even bothered plotting it. And Cubic simply collapse because the carriage profile of Starlink is incredibly hostile to normal TCP behavior. So if you actually want to push the rated capacity through Starlink, you need a protocol that doesn't behave like standard loss-based congestion control. You need to actually go to a model like BBR that is far more opportunistic in the way in which it takes available bandwidth and takes incredible sustained random loss and just simply pushes through it. And I think that's the end. Next slide. I believe that. No, okay. So Starlink, I don't think we've ever built this since about the 1960s or 70s in communication systems, because you've got this really high level of jitter, really high, and incredible levels of micro loss, not sustained burst loss, but just single packet events that lose. And that's not something we've optimized our flow control protocols for, because we've never seen it before. This isn't fiber, this isn't Kansas anymore. It's a completely different way of looking at it. Loss-based protocols, because we always thought, up until Starlink, that carriage is pretty good. And that what we're going to optimize TCP for is when I push the buffers to the point of overflow, I'm going way too fast and I need to back off. And that's the entire congestion control argument. How do I sensitize that algorithm? But that algorithm only works when the nature of the behavior is the same order of magnitude in time, right, as your round trip time. Yep. If you have highly variant carriage behavior, highly variant, and your round trip time is out there at 30, 40 milliseconds, you get failure, because the feedback control loop will overcompensate and simply go too slow. That's the only way it thinks it can survive, and you leave all this unused bandwidth on the floor. Bad idea. So loss-based algorithms simply pull back. So if you're using this for short-based transactions, you're not trying to keep the thing running for 3 hours at maximum speed, but you're even doing video buffer refresh, it'll basically work, because you're only throbbing at the link and then backing off. So even if it behaves like a dog, you really won't see it. But if you line up a terabyte of data and say, make it go through, you will notice. So Zoom's fine. Large data transfer, not fine. So the moral, I actually thought Quick would do better than it did. I believe Quick had a much higher SAC vector than standard cubic, but it behaves worse, so maybe I was wrong. Quick should have done better, it shouldn't. If you really want it to work using standard loss control TCP, use a large SAC window, because you're going to get loss and you want to repair it in flight. You don't want to back off. But better off, don't use loss-based congestion. Use BBR and just simply push through the entire system and you get much better throughput. Yay.
We have 4 people in the queue.
Oh, cool. That's right. They're not lining up the
So
microphone, are
please,
they?
Jen and Gori.
Lorenzo Colletti, super interesting. Thank you. Just a few points. I think speed test, I don't know if you're talking about speedtest.net. I think it uses multiple TCP connections at the same time, which means it'll sort of fudge all of this, right? Because you, oh, okay. Yeah.
I use speed test CLI.
Okay. I don't know how that works, but if it uses multiple TCP connections or fresh TCP connections every now and then, it'll be in that sweet spot at the beginning until when it does like slow start until it hits the first loss, right? Other things, I do wonder whether the 50 milliseconds is not because the packet is ours, but it's because if we actually expose 3.7 milliseconds, all of this stuff would just totally fall apart. If you expose this really high jitter to cubic, I think it'll just go. I think in particular, I think the cubic in a Linux kernel also looks at latency variation because it tries to detect sort of like congestion by that as well. I think, you know, I'm sure people can correct me, but again, if you expose this 10x latency delta, it will probably just like work really badly. So I wonder whether that's what's going on.
That's a really interesting point. Don't forget the entire business case for laying the Hibernia submarine cable across the transatlantic was 6 milliseconds faster than everyone else. So all of a sudden you have something up in the sky that is 50% faster than fiber. If only you could expose the raw propagation latency, they would take the entire world's low latency business, daytime traders, and simply monopolize it. And so I'm kind of surprised, and eyebrows are lifting, that they're actually holding on to the packets for much longer than propagation would suggest. And I agree in some ways that there is a trade-off going on here between, you know, FEC and a whole bunch of other conditions. But I thought the big game was going faster, and Starlink could, but it doesn't seem to.
With better, if you had BBR, it probably would.
Who knows? I do have BBR, and it does seem to fly.
Who knows? Maybe in a few years they'll sell a new class of service for the ultra low latency for 10 times the cost.
I wouldn't put it past them. It's a $1 trillion game, low latency. Yeah.
First of all, really interesting data. Cannot hear myself, but I hear the knock, so it works. Is there any documentation on how the physical layer works here? Because probably not. But you know, it's a satellite. It's a shared medium. You cannot do collision avoidance by listening for other people sending.
You know how this theory went that Google says nothing publicly? Compared to Starlink, they're chattery as hell. They tell you everything. Starlink tells nothing. So what you actually, all of this is reverse engineered in academic papers. There's nothing out there. So yes, it'd be nice if they published more about their protocols, their controller. I don't even know which satellite they're tracking anymore because they occluded that information. So all of this is second level engineering about what the hell are these guys doing?
Yeah, I expected that. So if you look at the upload latency, if you look at other protocols like DOCSIS, you cannot just all send random data, but you need to get an upload slot before you can actually send data if you send bigger chunks. So there may be multiple round trips involved with the satellite before you can actually send your packet. So it may be interesting to look at the physical protocols to do something similar and see if you can infer behavior like that in Starlink. Because what you may observe, what you observe with DOCSIS nowadays, is that if you are trickling data constantly, your latency is lower than if you actually are not actively sending data.
It's an interesting point. I suspect, and you know, they publish nothing, that the underlying technology is 5G femtocells in the sky with, you know, a lot more power, a lot more antenna, and a bit more control systems, but it's the underlying, the technology is very similar. The other thing I suspect that makes life bizarre is each spot beam isn't a square, it's actually a variant signal to noise ratio as it passes through. And so you actually find is even if you're tracking in those 15 seconds, you get an astonishing variation in signal to noise quality as the thing is zooming over. And that will affect the varying signal to noise, the clarity of the signal, and the amount of signal you can actually push through. So all of those bits of physics impact upon performance, you know, and I don't design this kind of crap for a living. I have no idea how it works. I'm at the protocol level going, wow, why is Cubic so crap at this? You know, so yes, trying to actually relate the two is a piece of guesswork right now.
But
But it is interesting. Your issue about if you pushed hard and try to see if there's latency, it's an interesting thought. What I've seen in the papers is that Starlink command each satellite to go to that user, that user, that user in 15-second increments. So there's this Starlink control system that simply schedules capacity to dishes. Yeah.
It's a mystery.
For the moment.
So, Gary Fairhurst, lovely to see the data. That's great. I've done measurements and know other people who've done measurements on Starlink, so it's great to have more. It's interesting to see how it's changing with time. You didn't cover the aspect like 6 months ago it was different. This 6 months it is different, etc. Because I think it is evolving. Unfortunately, it's evolving partly by satellite payload, so it depends which satellite is over you when you do your measurement, rather than, yeah, and we don't know which ones are which anymore, so this makes it really, really confusing. So good to have the data. I'm a little bit skeptical about people who present things on Quick and then use just one Pico Quick, which is a particularly esoteric version of Quick. So good to have data, but maybe you get a different data if you use a different different implementation.
There are papers out there on the variations between implementations of Quick, and these are fine papers. And what it points to is that once you lift a protocol from the kernel to the user space, all bets are off. Because your implementation, my implementation, will have different choices. And to think that somehow you and I adhere to standards even as religiously as vendors do, and they don't, is kind of wishful thinking. So yeah, you know, Quick is all over the floor.
And finally, BBR. BBR is a bandwidth estimation method. So it tries to use all the bandwidth for the flow. Whereas Cubic and Reno are capacity sharing mechanisms, anticipating that multiple people are going to be sharing the bandwidth. If you stack multiple BBR connections up, they don't always play well with other people or with themselves. So
that's a different pack and a different slide set. I do have that.
It is,
data,
yeah, and
yeah.
it is something that to be aware of when you tell people BBR is the best method, because BBR might be the best method for one case, and it might be brilliant, exactly the right for that case, and in a different scenario, maybe you want something else. So
I mentioned that hell is other people. I don't care about everyone else. It's all about my Starlink and my performance.
Just use BBR then. That will definitely help.
Absolutely.
Hi, Greg Choules, ISC. Thanks very much. That was very interesting, Jeff. I was just thinking about flow control algorithms and whether there's some scope for some research into industrial process control, because that's been going on for decades and decades. And, you know, there are some very complex bits and pieces out there, and you can just buy an off-the-shelf thing that just self-tunes and works it out for itself. But so there must be some, you know, very high power maths going on behind that has just been commoditized now. That could maybe be put to use in this kind of a situation where you don't understand what you're dealing with, but it can work it out for itself.
The philosophy of the design of TCP, I'm getting philosophical here, network people, so you know we're going to launch into is there a god of protocols? The philosophy of the design was trying to achieve two objectives. It was trying to make sure there was no slack bandwidth on the floor, that in the absence of everything else, the network capacity was used. But the second thing was, it was trying to be friendly to everyone else who was active at the same time. And the resultant sort of the Church of Berkeley TCP was this philosophical idea that as long as everyone approximately uses the same congestion control protocol, they'll end up being friendly to each other. And so you've kind of moved those two objectives. BBR threw out the second objective. It's not that friendly because its idea of using, you know, capacity was so totally different to the traditional model of TCP. And then when you start to talk about what's the feedback model that controls it, with Starlink, you're not on wires anymore. And the whole model of where TCP was does not fit in Starlink. You know, that's what we're seeing here. And then it's a case of, do I change the world for Starlink? Yeah, right, that ain't gonna happen. But how do I sort of integrate a Starlink link into a longer end-to-end connection is a really interesting question. Because, you know, there will be, I'm not sure how many folk, but at least 1 billion probably behind Starlink within a year or two if Mr. Musk has his way. And if it behaves like crap, then, you know, that's no good for everyone.
Thank you.
Yeah, thanks.
Lorenzo, clearly, servers clearly need to be able to change congestion algorithm within a given connection, see what works best. I leave that left as an exercise to the reader. I had a question actually. You pointed out this 15-second switch where you change. Right? What happens while it's switching? Does it lose packets that have two radios? Well, it tracks both of them at the same time?
Back. Forward. So that one.
Like, does it have to move the dish?
No, it doesn't. The dish hardly moves. Most of this is phased array. Next slide.
Oh, okay.
There's a red one here. That one. I'm pinging every second. Every second. So I should get 14 clean and 1 bad if it does a switch over, right? Yeah. But I don't get that. I kind of get this, oh, I dropped. And there's no persistent time signal behind that, the points where that 1 second ping actually goes away. And so it's kind of a mystery to me why. And the modem, Dishy, is telling me bugger all. You know, oh, I dropped a packet. No such report.
So it doesn't need time to lock onto the new signal or anything. It just
seems to pre-provision. It's a big phased array antenna, and while it's tracking one, it's getting ready for the next. So in theory, the switch over is seamless. In practice, not quite. But it's not related to switching. That loss profile is not a satellite switching loss. Otherwise, it'll be 15 seconds, bang, bang, bang.
Gary first again. Yeah, I concur. We don't see packet loss in handover. There is a small training interval, inevitably from the design of the modem, which you will see as it compensates for Doppler shift and retracts. This is not visible at the user layer with the protocol at all. You do see the 15-second differences when it hands over between the different orbital planes and different satellites. If you actually track very carefully the RTT variance, you can actually see it. But it's mainly smoothed out. This is an issue. No loss.
That one.
Yeah, that one.
I mean, it is impressive how well this works.
It's amazing it works at all.
Truly. Yeah.
Hi, Bob Hinded. Different question. So they have different types of dishes, you know, the user dishes. There's, you know, the one that's on a little platform, and then there's a larger flat one like for maritime. Do you know if there's any difference in performance?
There's two services out there. And Gary probably has more details than that, but there are two services. One is business, and it just seems to be a bigger dish with more antenna, which improves the signal to noise ratio. And I'm not sure if there's any change in the tracking behavior.
And the heater.
No?
And the bigger heater. The business.
A bigger heater, and you pay more money. And in theory, out comes more bandwidth. Underneath that, I think that's the only differences out there. The rest is how much protection you get from the elements, whether there's a dome, etc. But that's almost nothing to do with the signal itself. Maybe Gary has something.
It'd be interesting to see if this behavior changes with having the bigger antenna.
I have one of the bigger dishes if you want to run stuff from it.
Ooh.
My house is like near trees and stuff, so I had to buy the bigger one. And the trees went away. Yeah.
Sounds interesting, Warren. Gary, yeah, the maritime LEO terminals basically do a lot more Doppler shift compensation because the ships actually move the antenna base. And that is a huge issue in trying to get these satellites. So it makes more complicated electronics. If you get it right, then it doesn't change the signal.
I've been tracking the dish itself.
I mean, you shouldn't see this, right?
I had another animation of the dish actually says where the dish is facing, not the phased array antenna, just the dish. And it's pretty stable.
On a ship?
Not on a ship, on the Earth, where it's stable, you know, not in earthquake zones.
Yeah.
Yes.
Or in a normal place, the dish smoothly tracks from horizon to horizon. And this
No, it tracks 11 degrees.
just tracks 11 degrees.
Yeah.
This depends on where you are on the Earth's
No, it's the
surface, I think.
It's the 15-second time increment.
Yeah. Okay.
11
Anyway,
degrees is 15 seconds.
Anyway, the maritime terminal is better Doppler shift compensation.
Okay. Thank you all. If that's it, thank you.
Sweet. Anybody got any other last something? Oh, didn't you have an animation? Is it worth trying to find that and display it, or whatever you, if you want?
labs.apnet.net/Starlink. Labs.
Labs.apnet/Starlink.
Yeah, /Starlink. Animation time.
Pretty pictures.
Go down all the way to the bottom.
Whee!
Okay, so this is accelerated. It's not real time.
Share
something.
Performance plots. Yeah, that
I
looks
don't
like
know.
it.
Yeah.
Purdy. I don't know what it means, but purdy.
God, that's crap.
That's the thing with the scrolling and the thing and the. Yeah, actually, it is fairly.
For some reason the video completely. This is sort of accelerated time, but this is kind of the visibility. If you look up, Starlink, the dish will not look at the sun, and it will not look where the geostationaries are. So it will not actually track across the equatorial plane, which generally it picks. If you're in the northern hemisphere, it'll pick the northern hemisphere tracking, the top half. If you're in the southern hemisphere, it'll pick the southern, because there are more satellites there, because the pole is closer, to each other than the equator. But like I said, Starlink doesn't tell me which satellite it's tracking, so I wouldn't have a clue. But that's what it sees when it just looks up, which is cool.
Hi, Jeff. It's Tom from BT. I have just one quick question around the topology at the moment. Are they still using ground stations with Starlink, or have they switched to?
They're using both. And I had an interesting conversation with a gentleman from Mongolia, where they're actually doing remote schools over Starlink. But for reasons, there are no Earth stations in Ulaanbaatar or in Mongolia. There just aren't, and reasons. So they're lifting them across to Japan.
So inter-satellite?
Inter-satellite to Japan and then hauling them back. I think the Kiribati Islands in the Pacific. And if you wander into the bits of Australia that aren't burning, somewhere in the middle of nowhere, same kind of problem. There is no Earth station, within thousands of kilometers. You're doing the links already. So they do have it. The latencies lift from, we saw before, between 40 and about 70. They lift to about between 55 to about 90, which is not a lot, because
so it's
speed of light, they're not that far apart. Seems to work.
So the latency is, in general, worse when it's
only about 10 to 15 to 20 milliseconds worse.
Okay.
But the throughput and so on actually seems to be the same.
And does it improve on the jitter? Do you know?
Well, not. I haven't done extensive tests because I'm not in Mongolia.
And lastly, have you considered maybe trying any of the other constellations out there?
This is purely opportunistic. I just got an Intel NUC and put it right beside Dishy in someone's house, which is what I'm thinking here with Warren. And it's just been playtime. There's nothing terribly structured about this. I was just fascinated about, how fast does it go really?
Well, if I see an opportunity for you to try another one, I'll let you know.
Thank you. I'm sure we can arrange something. Thanks, Warren.
Hi, Tal, rural Vermonter, and I just wanted to say that I have a lot of direct experience with it, but not from a research perspective, because as a rural Vermonter with a really poor internet access, we have found it to be a godsend, right? Like it is, as a consumer who just wants to, my family just wants to surf the web and watch videos and everything, it's delightful.
Right. It's just when you'd line up a few terabytes of data and you look at the throughput and you go, why is throughput so crap?
Right.
That's when you find the thing falls apart. But short transactions, Zoom, all that kind of video stuff, it just seems to be seamless.
Right.
Yeah.
And so overall, I just wanted to
I'm
not trying to
Starlink.
sell it either. Like,
Yeah.
in fact, I'm also a member of the CV Fiber board where we're trying to get regional fiber in. But in practice, it does work shockingly well.
Yeah. I mean, the place I was using it, I was a wireless link to a wireless link to a wireless link to a wireless link to a DS3 to the internet. And the wireless links are literally like 802.11 links. During the day, it would be 30 megabits per second. In the evenings, when other people used it, I would get literally like 15 kilobits per second. And Starlink made my life less sucky.
Yeah.
It's not perfect, but yeah. This was fascinating. Thank you.
Thank you. Thanks.
And that is the end of today. Oh, everyone, don't forget there will be another IEPG meeting in IETF119 Brisbane, wherever the hell we are next time. Please think of interesting things to present.